All right, everybody, welcome to the third screencast for Chapter 6. In this screencast, we're going to look at how we can use dummy variables to help us when we have categorical variables, right? So a categorical variable is going to be something like eye color, right? Blue eyes, brown eyes, green eyes, hazel eyes, other, right? There's a bunch of categories we could think of. Or hair color, or your year at Mercer, freshman, sophomore, junior, senior. Those are categorical variables. And what we're going to see is you can't just toss those right into your regression as is, right? We're going to have to transform them first. Upside is, if you're doing this in R will do this for you as long as you tell R, hey, this variable is a categorical variable. I know I've got numbers here. I know I've coded blue eyes as 1, brown eyes as 2, green eyes as 3, other eye colors as 4, but you can't treat those as numbers, right? You've got to convert them first. If you tell R, hey, this is a categorical variable, and in the language of R, it calls those factors. You say, hey, this is a factor. It will do it for you, but we need to know what's going on under the hood because there's a little bit of trickiness here going on, all right? So a categorical variable is one that does not have any specific ordering, all right? I call these unordered categorical variables, all right? I like to be very specific here. So while the book, Bailey, just calls these categorical, I call them unordered categorical variables, all right? Because the other kind, the ordered categorical variables, are still categorical. So I use unordered categorical and ordered categorical. Bailey uses categorical, and then he uses ordinal or something like that. But first, let's get this one down before we move to the next one. An unordered categorical variable, again, this is what I prefer, doesn't have a specific ordering. So if we had a data set and one of our variables was religion or race or industry or favorite fast food or whatever it is, if those things don't really have an order, right? There's no ordering to religion, right? If I have all the major religions in the U.S. in, say, a survey, there's no this religion gets a 1, this religion gets a 2. It's just a convenience, right? It's not an actual order. Same thing for race, same thing for different industries that companies could be in, same thing for different foods. Eye color is the same way, right? There's no real order to them. So that's an unordered categorical variable. The other type of categorical variable we're going to deal with are ordinal, or what I call ordered categorical variables. These are variables where it is categorical, right? But the categories have a logical order. So an example might be education level. In a lot of surveys, they don't ask people how many years of education do you have, right? You could do it that way. What they usually ask them is, please tell me which category you fit in. No high school diploma, some college, college grad, or graduate degree. And they code it something like this, 1 through 5. But we can't really just use these numbers as is. Why? Well, what's the difference between 3 and 1? Well, if it's a real measure of something, 3 apples and 1 apple, well, the difference is 2 apples. But what's the difference between some college and no high school diploma? It's not a 2, right? And you can see that by thinking about, well, what's the difference between a graduate degree and some college? That's also 2 different in this coding, but there's no reason to think that those would have the same effect on whatever your dependent variable is. So it's a common mistake that people use with ordered categorical variables. Usually with unordered, they don't make this mistake. With unordered, most people realize if I have eye color and blue is 1, brown is 2, green eyes is 3, I know I can't just throw that in a regression. That doesn't make a whole lot of sense. But some people are tempted to think that because there is an order here, you know, going from 1 to 5 is more education, they want to throw that in as is. And you actually cannot do that. It will not work that way. You will get results that are not correct because R or whatever statistical program you're using is going to assume I can do math with these numbers like they are pounds of sugar or dollars or values of weight or height. With those things, you can do math on them. They're continuous variables. The subtraction, multiplication, those the results of those mathematical operations have meaning. Here, the result of mathematical operations on these values doesn't have any real meaning. All right, we could not put any stock in the fact that the difference here is 2 and the difference here is also 2. We couldn't say those differences in education levels are the same with any sort of meaning. So we're going to actually treat these the same in this class, whether it's ordered or unordered. Now, in some other higher level statistical classes, there are statistical techniques where you can take advantage of the fact that there's some extra information here because there is an order. We're not going to do that in this class. We're going to treat unordered and ordered more or less the same for the purposes of this class. So the best way to get our heads around this is, let's just start with an example. All right. So we've got a data set and we've got wages, and we want to know whether or not wages are higher in different regions of the U.S. And for this particular data set, we have a variable called region. And region is coded as, if you're in the Northwest, you get a 1. If you're in the Midwest, you get a 2. If you're in the South, you get a 3. And if you're in the West, you get a 4. All right. So we can't just run this regression. All right. We cannot just take that column region that has the variables coded this way and toss that in. By coding Midwest as 2, we would be implying that that is somehow more than Northeast, which equals 1. And that doesn't make a whole lot of sense, all right? And we would also further be implying that the difference between Midwest and Northeast is the same as the difference between Midwest and South. And there's no reason to expect that the effect of those being in those different categories is going to be constant, all right, as we move from the different regions. So instead of region, we have to use a set of dummy variables. We need to convert region into a set of 4 dummy variables. All right. Now, R is going to do this for you. What we would do in R is we would say, hey, R, region is not a continuous variable. It's not even a counting variable. It's not even an integer level variable. It is a categorical variable. In R, it's called a factor. Other statistical software has different ways of doing this. But we would say, hey, R, make sure region is a category. And when we use it, it would do everything for us. But we need to know what that means. What is it going to do for us? And what it's going to do is it's going to create a set of dummy variables for each value of region. So in other words, it's going to create a column called Northeast, a binary dummy variable for Northeast, a binary dummy variable for Midwest, a binary dummy variable for South, and a binary dummy variable for West. And that is what we're going to use in the regression, all right? So we can't use this, right? We can't just throw region in as is. So we create these dummy variables, but we have to be careful or we're going to have perfect multicollinearity. What was multicollinearity? Multicollinearity was when the right-hand side variables are highly correlated with one another. And it's a problem. It blows up the width of the hypothetical distribution of beta 1 hat, and it makes it hard to find statistical significance. If we included all 4 variables, we would have perfect multicollinearity, and it's not just bad, it's so bad that you can't mathematically calculate beta 1 hat. In fact, R would throw one out for you. It would just say, nope, can't do that math. I'm going to randomly toss one of the categories for you. But that's what this would look like if we tried to run the regression with all 4 dummy variables in there. So we can't do this either, all right? We would have perfect multicollinearity, and the mathematics of the linear regression, the calculation of beta 0 hat and beta 1 hat by that formula that we've learned earlier just would not calculate, all right? It's sort of like, in fact, it's not sort of like, it is like if you have a system of equations and you're trying to solve for variables, you have to have the same number or more equations than you have unknowns, right? You can't solve a system of equations with 4 variables and only 3 equations, right? You can't have more unknowns than you have equations, right? It won't work. If that explanation meant something to you, good. If it didn't, just pretend I didn't say it. But that's mathematically to give you a sense of what's going on underneath the hood as to why you can't run this calculation, right? Because I'm solving for 1, 2, 3, 4, 5 values with only 4 equations, basically, underneath the hood. So we can't do that. So we have to drop one of the categories, all right? And it doesn't matter which one you drop. Spoiler alert. The information you get back from the regression is the same no matter which one you drop, all right? But we have to drop one of them. Sometimes for particular questions, it's going to make sense which of the new set of dummy variables that you've created from your old categorical variable, which one do I want to drop as the baseline? You hear it's called that often, the baseline group. But let's look at a couple different examples here. So we're going to pick a reference category or the excluded category or the baseline category, and we're going to drop it, all right? And we're only going to include the other categories, all right? The beta coefficients on the remaining dummy variables, the ones that we do include, are going to be relative to the reference category, all right? So let's take this one first. So we are dropping West as our excluded category, all right? So we're going to look at how wages differ across different regions of the U.S., and we're including Northwest, Midwest, and South, right? But we're not including West. So here is the result for that regression, all right? So let's see what we have here. So as you can see, I'm going to show you all 4 different ways we could have done this, right? We have 4 different categories. This is what we wanted to run, but we can't. So I'm going to run it by first dropping West, then I'm going to drop South, then Northeast, and then Midwest. Sorry, Northwest, then Midwest. I'm going to drop one at a time. Actually, I don't remember if that's the exact order, but you get the idea. I'm going to drop one variable at a time. So first, here we exclude West. So that's why you don't see a beta coefficient. You don't see a slope coefficient for West. What we do see it for is Northeast, Midwest, South, and the constant, all right? So the left column here has West as the excluded variable. And for now, we're just ignoring this stuff. That's why I have it grayed out there for you. So the constant here is going to be the average of Y. What was Y? Y is wages for the excluded group. So even though I left out West, I've got information about them right here. So this is the information for the West. This is, and it's very much like the way we interpreted this for the difference in means test. This is the average value of the dependent variable. So it's the average of Y, or Y bar. It's the average wages for the people in the West. So on average, people in the West make $12.50 an hour, or at least the people in our data set. All right, so women in the West, this was a data set for only women. Sorry, I forgot to mention that earlier. Women in the West make $12.50 per hour on average. So this, just like it was for the difference in means test, the constant beta naught hat is the average value of the dependent variable for the group we left out, the 0 group. Notice, people in the West got a 0 for South, they got a 0 for Midwest, and they got a 0 for Northeast, right? Because they don't live in the South, they don't live in the Midwest, they don't live in the Northeast. So this is the average for that excluded group or that baseline group. How do I now interpret these betas, all right? Well, notice, first of all of them are statistically significant, right? They're all bigger than 2. So what do these values of beta 1 hat, beta 2 hat, and beta 3 hat mean? All right. Well, beta 1 hat is the difference in Y, the average difference between the baseline category and this category. So this is the difference between the people in the West average wages and people in the Northeast average wages. So people in the Northeast on average make $2.02 more than people in the West. So you interpret the beta coefficients in reference to the omitted group. So beta 1 hat plus beta naught hat is the average wages for this group. So if I add them together, I get 14.52. So 14.52 is the average wages of people in the Northeast. Notice those steps are very, very similar to what we did for the difference in means test. So coefficient beta 1 hat, 2.02, means women in the Northeast make $2.02 more than those in the West, which is $14.52 an hour. The coefficient on beta 2 is the difference in the dependent variable wages between the dummy category X2, or people in the Midwest, and the excluded category, people in the West. So beta 0 hat plus beta 2 hat is the average wages for the Midwest in this regression. So a coefficient of beta 2 hat equals negative 1.59. It is statistically significant. That's why we're doing this interpretation. So women in the Midwest made $1.59 less than those in the West, which would be $10.91 per hour. All right. So you can already get a sense of it doesn't really matter which category I drop. I can still recover all of the same information. I can recover the difference between being in one category versus the other, and I can recover the average value of the dependent variable for that group. All right. So if I want to know for the West, what is the average? It's 12.50. If I want to know the difference between people in the West and South, I know that it's negative. It's going to be $2.13 less. All right, so what if I now run a different version of the model? So again, for now, just ignore all this stuff and ignore all this stuff. All right, we're just focusing on running the regression with South as the excluded category. So this is the regression where wages sub I equals beta 0 hat plus beta 1 Northeast, beta 2 Midwest, beta 3 West. South is omitted, all right? So the constant here, 10.37, it is statistically significant. This is the average for the omitted group. This is the average for women in the South. So on average, women in the South made, at least for this data set when it was taken, $10.37 per hour on average. What about the coefficient for Northeast? So how do I interpret it? We always interpret these sets of dummy variables, the betas on them, as the difference between this group and the group that gets a 1 for this variable and the omitted group, which is women in the South. So 4.15 means women in the Northeast make $4.15 more than women in the South, which is $14.52. I just add together beta 0 hat and beta 1 hat, and I get 14.52, which is the average for that group. Notice it's the same thing I got when I did it over here. I added for the West average to the difference between the West and Northeast, and I got 14.52. All of these columns contain the same information. You just have to remember what the omitted group is and interpret the results accordingly. What about the coefficient here on beta hat 3? That would be down here. That would be the West. So means that women in the West make $2.13 more than women in the South, right? You always interpret the beta in reference to the omitted category. And to find out what the average wages for the West would be, I simply add the two together and I get 12.50. And that was indeed when we ran the alternative specification, the alternative version of the model with West excluded, we saw that that was indeed the average wages in the West. All right. So again, maybe beating a dead horse here, but the information is the same. So if you do this, if you have a situation where you have a categorical variable, you're going to have to decide which one to exclude. Now you can let R do it for you, and a lot of people will do that if this categorical variable is a control variable, because then I'm not so concerned with which category gets dropped. You can just tell R, this is a factor, this is a control variable. I'm sorry, this is a factor. For example, here region. Region is a factor. It's categorical. You can then throw it in the regression just like always, but R will say, wait a minute, this is a categorical variable. I'm going to create a set of dummies for you, and I'm going to toss one and include the other three. And it'll just pick one. all right? It has a little algorithm for picking which one is dropped. If it's a control variable region, you probably don't care. But if it's your independent variable of interest, as it is in this regression, you might want to pick. So you may want to create those variables manually. Now, you don't have to literally create them manually. You don't have to generate four new variables and go in and put a 1 and 0 by hand. There are R commands, or if you're doing it in Stata commands, whatever software you're using, there are commands that will let you automatically generate the set of dummy variables. So the fact that women in the Northeast make 14.52 can be seen no matter which version of the model you're using. Here I add 12.50. Well, I don't add it to anything. I see that that is the value for the average wages for people in the West. Here I add the intercept, which is the average for the South, to the West. Here I would add the intercept here, which is the average wages for people in the Midwest. Notice that's the omitted. To the West, I still get 12.50. Over here, I add 14.52. This would be the average wages for people in the Northeast. I add that to the value for West, which is a negative 0.20, and I still get 12.50. So I can always recover the average value for any group just by doing a little bit of math. Or, here's the thing, if there's one particular region you really care about the most, use that as the excluded category. Much like we said with the difference of means test, sometimes it makes the most sense to make the 0 group, or here make the excluded group, the one you're most interested in, because you get the information about it right here in the constant without having to do any transformation or any math. All right, so the fact that women in the West made 12.5 can be determined no matter which region is the reference. We can always find what the average is by adding the two relevant betas. In general, different choices of reference categories will change the coefficients values, but the effect we're finding, the substance of what we're seeing, is the same. So you can exclude whatever category you want, but you must be careful when interpreting things to make sure you remember what was the reference category, right? It would be a big mistake to say, let's take this one for example, this middle column B, and say the effect of being in the Northeast is a $4.15 higher wage. You have to say it's 4.15 cents higher than the South. You have to include the excluded category in the interpretation. So let's look at a case study here. Let's ask the question, when do countries tax wealth? So more specifically, historically, and we're going way back here, historically, does universal male suffrage affect inheritance taxes in different countries? All right. Does increasing the franchise or the right to vote lead to more people voting for inheritance taxes, right? Because what's the story here? Well, way back, 1700s or something like that, in most places that did have voting, who was voting? Wealthy males, for the most part. Wealthy males of the dominant ethnic group and dominant religion, for the most part, in different countries, right? Only a limited subset of people were voting. So you can imagine those people don't love the idea of an inheritance tax. These are the kind of people who have inheritances to leave. They're the wealthy folks. So the question here is, as we expand the franchise, starting with only those wealthy males of the dominant ethnic group and dominant religion to all males, right? Do we see more inheritance taxes in different countries? All right. That was the research question for this particular research paper. All right. So here might be our first approach at that. All right. So inheritance tax, it's going to be a percentage. It's going to be the percent of an inheritance that's taxed. And here's going to be universal male suffrage. So we're going to look at one of these indices that are created by different groups, and we're going to say countries that have universal male suffrage are going to get a 1, and countries that don't have universal male suffrage are going to get a 0. So, and we're going to just rely on the data that's given to us. You can guess that the people who put together this measure had to make some judgment calls. What does it mean to have universal male suffrage? So for example, in the South during the Civil Rights era, technically on paper, there was universal male suffrage, right? All males were supposed to be able to vote. All females too, for that matter, by the Civil Rights Movement. But was it in fact universal male suffrage? I'm not sure how this particular data set coded that, but we're going to just take the data as it was given to us. But you're right, if you were thinking about, well, how did they code that? There's a lot of detail there that we're just going to ignore because it's just an example for us. But if you were dealing with this research area, you'd have to think really hard about how that variable is coded, all right? So here is what our example looks like. So these folks here, Sheev and Stasovich, I'm not sure how you say it, we're going back to 1816, 19 countries over, what we're looking at here, 184 years, something like that. So this is why we have to use universal male suffrage, because almost no countries would have had it in 1816, and lots of countries may have it by 2000, but if we used universal suffrage, right, we wouldn't have a whole lot of data. All right, so they decided for their question, and I've never read the paper, I'm not sure exactly what the context of their question was, but they're using universal male suffrage. All right, so here is the result of this bivariate regression, right? Inheritance tax, and they also probably had to do a lot of work to make inheritance tax comparable across different countries. But again, that's not for this sort of class, how to deal with those measures. We're just taking their measures as given. So does it appear in this bivariate regression, which would be a difference in means test, right? It would be, do on average countries with universal male suffrage have higher or lower inheritance taxes? So here's the result. What is this? This is the difference between being in the 0 group, not having universal male suffrage in a particular year, and being in the 1 group, a country having universal male suffrage in a given year. It is statistically significant, and what we can see is the difference is 19.33%. So the inheritance tax in countries with universal male suffrage, the difference in the mean inheritance tax across those two groups is 19.33%. What is the constant here? Well, the constant is the average inheritance tax in countries that don't have universal male suffrage in that particular year. All right, so that would have been 4.75. What is the average inheritance tax for countries that did have universal male suffrage in a particular year? Well, I just add these two together to get that. And I think I have it on a slide in a second. I'm not great with that kind of mental math, but it looks like 24 point something or another. But anyways, that would be the average inheritance tax rate in those countries, the countries that got the 1 for universal male suffrage. Oh, here we go. Yeah, I do have it in here. So that's the coefficient. It is statistically significant. And we can say, yes, there is a difference in the mean value. All right, but we still may not be able to say anything, make any sort of claim that we have any causal evidence, right? Because we might have some endogeneity here. Countries without universal male suffrage, 4.75%. Countries with universal male suffrage, I was close, 24 point. Looks like I went the wrong direction with my addition, but anyways, 24.07 is the average inheritance tax in countries with universal male suffrage. But maybe there's omitted variable bias, right? Because inheritance taxes worldwide increased over time, right? Even in places where voting didn't change, right? Taxes have generally gone up over time. The franchise, the percentage of people in a country that are allowed to vote has also gone up over time. So those two things may just be both going up over time, and there may be no real causal effect, right? It could just be a time trend, right? And when you're dealing with time series data, you guys in finance, macroeconomics, lots and lots of time series data where your rows are units of time. You have to think about this a lot. Is it just the fact that these two variables are both going up over time and it has nothing to do with any relationship between the two? So we need to take that into account here. So here is what these two look like. So here I've got year on the horizontal axis. Again, I would have probably put year on the horizontal in both cases, but we can see that there's probably a correlation between year and inheritance taxes, and there's probably a correlation between year and universal male suffrage. Both of these things look like there is a correlation. All right, so if I left out year as a control, I might think I have some sort of causal effect here when I really don't. All right. So, and again, I'm jittering the data here on this just so you can see that where all of these plots are in the scatter plot. So year is associated with changes in both the independent and dependent variable. So if I leave it out in the error term, I've got classic omitted variable bias. My beta 1 hat is estimated with bias. I can't trust it. I can't even trust the statistical significance in some cases if I'm trying to make a causal claim. All right, so let's throw year in here. Now there's a couple of ways you can do this, including year. We're just going to include year as a continuous variable. Actually, it's an integer variable, but you treat it the same way. We're not including year here as a category. All right. Now, if you only had a couple of years, you might think about the pros and cons of treating year as categorical. But for us, we've got, what we say, 184, 183 years or whatever it is. We're going to treat year as just a regular old integer level variable. We can just throw it in as is. We don't have to tell R anything special, because the difference between the year 1990 and 2000 is the same as 1890 and 1900. It's 10 years, and that has meaning. So we will just treat it as a regular old counting variable. Okay, so now we can include that and control. What do we see? All right, and in fact, we're going to do a bunch of different versions. We're also going to control for several other things, including region here. All right, but first, let's just take this first version. This is our original bivariate regression. This is what we've already seen. This was the difference in means test. All right. Next, what we're going to do here is this is our controlled difference in means test, our conditional difference in means test. We want to know if there's a difference in countries that have universal male suffrage in a given year and countries that don't have universal male suffrage in a given year, but we want to control for that year effect, right? That increasing of year over time to pull out what could be something that would cause us to have an endogeneity. So beta 1 was 19.33 by itself. That is truly the difference of those two groups. But now when we control for year, look what happens. Now all of the statistical significance is gone. All right? We are not statistically significant. Once we controlled for year, there was no statistically significant difference between the two. So it could be the case that all that is happening when we see this difference here between the two groups is, yeah, it's true that countries without universal male suffrage have lower inheritance taxes than countries with an inheritance tax in a given year. But the reason we see that difference is just because over time, both of those variables went up, right? The number of countries with universal male suffrage and the percentage of inheritance taxes both went up over time. And now we no longer see a statistically significant effect, all right? Tiny t statistics, we can't reject the null that universal male suffrage is doing nothing here, that it really just is the passage of time. All right. What about now? Let's look at some other variables that these two researchers wanted to look at. So here we're in this column B. All right. So we're looking at, well, what about whether or not the country is at war? Because if a country's at war, often you see taxes going up. So war could be correlated with the dependent variable. So war could be in the error term of the regression. But also, countries with universal male suffrage are usually less likely to go to war. This is a relatively robust, stylized fact that we see across different countries. The more people you let vote, the less likely countries go to war, right? When you start letting all males vote, well, a lot of those males are the ones you'd be sending out to fight the war, right? It's usually not those original wealthy landowning men of the dominant religion and dominant ethnic group that usually get sent off to war, right? So usually as the franchise expands, and especially once it expands to everyone in the society, you tend to see less instances of going to war. So plausibly that could be correlated with both. So if we include it, well, what happens now that we include that variable? Well, notice we're still not statistically significant, right? So we didn't get it back, right? The problem here would be, oh yeah, year made it go away, but maybe I still have another omitted variable bias problem and I can't trust this. So now we've included war. All right, well, what about region? Maybe the region of the world is a factor here. Now, why are we including region? It's probably not the case that where a country is geographically on the map, the longitude and latitude coordinates of the centroid of a given country has much to do with whether or not it has universal male suffrage or what its inheritance taxes are. But what is correlated with region of the world are legal systems, right? Legal systems tend to develop in particular countries, and they tend to spread out according to different, usually colonization, right? Usually you see the spread of legal systems through colonial imperialism, right? So, for example, in the United States, we have the common law system based on the Old English common law. Why? We were a colony of England, all right? Except for Louisiana, they got the Napoleonic Code down there. They got the civil law. It's a little weird, but why do they have that at the state level? Well, it's because that's what France was the place that originally was the dominant government that colonized that area of the country. And so the reason we include region here is because it's a proxy. It's a stand-in for the legal system, possibly. Countries in Europe tend to share similar legal systems. Not completely, right? Continental Europe and England could be different, but for the purposes of this is what these researchers did, all right? Asia, North America, right? So these were the different categories. So instead of just including, so let's say they had region as the variable, Europe was 1, Asia was 2, Australia, New Zealand was 3, North America was 4. Can you include that in the regression? No, you cannot include that in the regression. It would not help you, all right? Even as a control variable, it would do bad things for you. So you would create a set of dummy variables and include all but one of them. Here in column C, we can see this is the version where we've left North America out as the reference category. So what happens here? Well, look, the t variable went down again. We're now moving further away from statistical significance, all right? By including region, by including that omitted variable, possibly omitted variable of legal system, oh, and again, I forgot to say, why might legal system be an omitted variable? Well, legal system tends to go with the franchise, with who can vote and who can't. And the legal system also tends to go with the size of taxes. Those things are correlated. So this column presupposes that if we left out the legal system, we might have omitted variable bias. But even once controlling for it, we still don't have any statistical significance. This is just a different version of that same model where we've now omitted Australia and New Zealand. So all of the information is the same. You can notice that what doesn't change here is the coefficient on the variables that are not one of those regions. Those coefficients and their statistical significance don't change according to which one you drop in the region control variables. So C and D are the same. They have the same information. Even though these coefficients here, like for Asia, oh, sorry, I don't want that. These coefficients for Asia are the different. Remember, it's because we've used a different drop category. So, but we're not going to interpret them anyways because they're control variables, so you don't have to worry about that too much. All right. Here I'm just giving you a reminder of how you interpret these. So Europe is compared to North America in C, and Europe is compared to Australia, New Zealand in D. So let's look at that here. Oh, went too far. Let's look at Europe here. There we go. So these coefficients look different, but remember, the baseline here, the constant here, this is the average for North America, and this is the average for New Zealand here. So Europe's tax is 5.65% below North America's in this regression. Remember, substantive results don't change according to which category you drop when you have one of these categorical variables in your regression and you're including all but one baseline category. You just have to be careful with interpretation. So this is a really nice way to show multiple models. All right, and if any of you want to do this in your paper, those of you that are doing the statistical analysis, be happy to show you how to do this. If you're running multiple versions of your model, you're not at all required to do that for this class, but we get this nice confidence interval with 0. So all of these are statistically insignificant, but the bivariate model was statistically significant. So the difference of means test was different. Yes, there is a difference of means. But once we did a conditional difference of means, it wasn't statistically significant. And once we included the regions and all of those other variables, we never got statistical significance. And that's what all these different slides say. And so you have those for studying purposes. All right, so that's the end of section 3. We have one more section for our use of dummy variables, and that's going to be for interaction variables. We're going to look at what happens if I want to know not just whether two groups differ in a parallel way, right? Remember when we plotted both of those best fit lines, we got parallel lines in the section 6.2. But what if I want to know, is there an interaction between the dummy variable and the continuous variable? And we'll see that in section 4.